Hi, Danielle Dickinson here for Saturday Morning Astrophysics at Purdue. If you have ever considered doing an experiment to measure the speed of light, you know that there are a lot of examples out there on the web that illustrate various procedures using an ordinary microwave oven. Some demonstrators have attempted this with chocolate bars, others cheese, some marshmallows, and various other materials, some of which have more merit than others. I have a few eager students here who have been experimenting with various materials and different procedures, and this is what we have found to give the best results.
Hi, I'm Kaustub.
And I'm Grace.
Let's see what they came up with. So how are we going to measure the speed of light with a microwave? What were those two quantities that we needed to measure again?
The frequency and the wavelength of the light.
We can find the frequency in the microwave schematics. So how can we find the wavelength?
Well, we can't see the wave, but we know there will be a standing wave inside the microwave, so maybe we can see its effects.
If we put something in the microwave, we can see how it melts and if some parts get hotter than the others.
We would need to remove the turntable though.
Yes, because we want uneven heating and we can see how the waves affect different parts of it.
So if we put something flat in the microwave, we can use where it melts and doesn't melt to see the distance of the wave by where the nodes and antinodes would have been.
Yes, that's exactly what we're gonna do. Now, let's go to the lab. This is the microwave that we're going to be performing our experiment in. How do we need to prep our microwave before we get started?
Take out the turntable.
Yep. So we are going to take out this center plate, the two components that make it turn. We are now going to flip over our plate so it sits nice and flat on the floor of our microwave. To get the best results, we want to lift the chocolate chips up. We are going to use two 400 milliliter beakers. Not only will this place a flat surface to put the plates upon, it'll lift it up closer to the top. Who wants to go first?
I'll go first.
All right, so go ahead and open your bag of semi-sweet chocolate chips.
I got this, trust me. I'm a big boy.
There you go. And pour it on the plate. We want a nice even layer. Try not to pack it down, but you do want to smooth it out. So for best results, we are going to microwave this for about a minute. All right, when you take the chocolate chips out, you'll notice there are melted regions and there are non-melted regions.
So these more gooey spots are where the antinodes of the waves were, and the parts that didn't melt correspond to the nodes.
Great. So now that we have this, how do we measure the wavelength?
We can measure the distance between antinodes.
How many wavelengths would the distance between two antinodes be?
Well, if we look at a wave has both a peak and a valley. One wave has both parts, therefore one wave would have three antinodes. The distance between two antinodes would be half a wavelength. Can I do this with a chocolate bar too?
Yep, you can do it with a chocolate bar, but when you open it, put it on the plate so the flat side is up. Perfect. So we're gonna put it in the microwave for about 25 seconds. And it's important to remember that when we take it out of the microwave, the chocolate will continue to melt. So we don't want to microwave it for too long so we can see the hot spots where the antinodes are. Ooh. Oh, yay.
So I see 1, 2, maybe 3 hot spots, but we're gonna just ignore that one since we can't quite see the middle. We're gonna focus on these two right here. And then if I measure the distance between the center of this one to the center of this one, I get about 7.5 centimeters.
I got about 6 centimeters.
Wonderful. So now that we have our half wavelengths, we are going to multiply that by 2 to make our wavelength. So how are we going to get speed?
Speed is wavelength times frequency.
Yes, exactly. We're going to turn to our microwave and check the back. And the schematics note that the frequency of the microwave is 2,450 megahertz. We are going to find the average wavelength from our two measurements, which is
0.135 meters,
and multiply that by the frequency, and we get a speed of light of
3.31 times 10 to the 8 meters per second.
Fantastic. That's really close to the actual speed of light, which is 2.99 times 10 to the 8 meters per second. Here's what we learned. Marshmallows didn't turn out so well. They expanded way too much, and we couldn't measure the center of the antinode. Chocolate bars worked a little bit better. They created nice melted spots on the smooth back of the bar, but the chocolate bar didn't cover a broad enough area. To get a broader area, we spread a single layer of chocolate chips on a large, oval-shaped paper plate. This increased the number of antinodes and provided a more accurate measurement of the wavelength. This was our greatest success. A significant discovery came in the form of us elevating the plate closer to the top of the microwave. We did this with 400 milliliter beakers, but you could use this with ceramic cups or mugs. With our 900 watt microwave, 20 seconds was good for the chocolate bar to melt, and for the chocolate chips, about 1 minute with full power was perfect. We hope you found this video on measuring the speed of light informative, and we look forward to you trying it yourself. Thank you so much for watching, and we hope you'll follow us for more activities, lessons, and demonstrations from Saturday morning astrophysics at Purdue.